It is the 5th of September 2025, approximately 7:55 a.m. And we are going to continue going along Dunning-Kruger's exercises, starting with exercise 19 for this lecture slash review slash whichever thing you might want to call it. We're just going to be looking at the lecture. So we're just going to be looking at the exercises. So exercise 19, let X be an element of G for G a group, and let A be within the positive integers. So we're asked to first prove that x to the a plus b is equal to x to the a times x to the b, and x to the a, well, open parentheses x to the a, close parentheses x to the b, which is equal to x to the ab. Prove that open parentheses x to the a, close parentheses to the negative 1 is equal to x to the negative a. Establish part 1 for arbitrary integers. A and B with positive, arbitrary means arbitrary, so positive, negative, or 0. Right. So let's get into that. Well, we'll start with some intuition, and then we'll get into something a bit more rigorous after the intuition is mentioned. So, intuitively speaking, read x to the power n as n copies of x multiplied in a row. X to the 0 equals 1, x to the negative n equals, open parentheses, x to the negative 1, close parentheses, to the power n. For instance, and then a plus b copies should split as a copies followed by b copies, and repeating a block of a copies b times gives ab copies. Inverse is flip each copy to x to the negative 1 and reverse the order, yielding, open parentheses, x to the power a, close parentheses, to the negative 1, which is equal to, open parentheses, x to the negative 1, close parentheses, x to the a, open parentheses, x to the negative 1, close parentheses, to the power a, which is equal to x to the negative a. So let's look at this more rigorously. So we proceed part by part. Showing each string of equalities explicitly. So for A, for part 1, we'll just call that A, because that's how it is in the book. I just put it into 1, 2, 3 to show that there are 3 parts to this. But for A, B within the set, within the positive integers, x to the a plus b is equal to xa times xb. This is what we want to prove. And open parentheses, x to the a, close parentheses, to the power b is equal to x to the ab. So let's write x to the power a is equal to x to the on and on and on until we run out of a factors. And x to the b is equal to x times all the way up until we run out of b factors. What can we say? What can we say then? Well, then x to the a times x to the b is equal to x to the, until we run out of a factors. Well, x times x until we run out of a factors, and then, well, that's multiplied by x until we run out of b factors, which is equal to, of course, as you would imagine, x multiplied by itself until we run out of a plus b factors, which of course would be equal to x to the a plus b. So similarly, open parentheses, x to the a to the power b is the product of b copies of x to the a. So what we can say here, because the first part has two parts, right? So because we have that and, we proceed, we've looked at this, this shows that it holds here. Now let's look at this case in which we look at the product of b copies of x to the a. So we have open parentheses x to the a close parentheses to the power b is equal to open parentheses x to the a times itself b factors, the order of b factors many times. So that's what we're left with there. Now, each of what this equals is x times itself, right? X times itself to the order of a factors many times in each of these parentheses, each of these parenthetical groupings, not group official, but groupings. And so this is still b blocks, right? This is still b blocks. This is still what we had up there, which is equal to x times itself to the a times b, the order of a times b many times, which is equal to x to the ab. So that holds in this group. Now we're going to move on to the next part after I check it on the camera. Good to go. Okay, now moving on to the second part, which we'll just call part B because that's what it is, and then for a within the positive integers greater than 0, we have x to the a to the negative 1 is equal to x to the negative a. So let's recall x to the negative a is equal to open parentheses, x to the negative 1 to the power of a by definition of negative powers. So we show x to the power of, open parentheses, x to the power of a, close parentheses, to the power of negative 1 is equal to, open parentheses, x to the negative 1 to the power of a by induction on a. So we start with a base case, right? So base is equal to, well, in the base, a is equal to 1. And for that we say, open parentheses, x to the power of 1, close parentheses, to the power of negative 1 is equal to x to the power of negative 1, which is equal to, open parentheses, x to the power of negative 1, close parentheses, to the power of 1. Now, let's look at the inductive step. This is interesting because whenever we look at algorithm analysis, like this would be a recursive step for sorting stuff, merge sort, but I'm not talking about that right now. Inductive step. So assume, right, so this is the inductive hypothesis, assume open parentheses x to the power k, close parentheses to power negative 1, it is equal to open parentheses x to the negative 1, close parentheses k for some k greater than or equal to 1. Then open parentheses x to the power of k plus 1, close parentheses, times open parentheses x to the power of negative 1, close parentheses, to the power of k plus 1 is equal to open parentheses open parentheses x to the k, close parentheses, times x, close parentheses, times open parentheses x to the negative 1, open parentheses x to the power of negative 1, close parentheses, to the power of k, close parentheses, which is equal to x to the power of k, open parentheses x. By the way, the reason I'm saying this is because the parentheses are going to matter. Parentheses are going to matter a lot. They're in about 2 sections. Also, it's like, if you were deaf and stuff, this is a thing just with like YouTube and like just publishing stuff in general. It's like, well, it's like requires some sort of auditory thing. It's kind of nice. It's kind of nice if you're able to like. I don't recommend listening to what I'm saying if you are deaf, like, but if there was, you know, it wouldn't hurt to just say it. But and it's easy for me, and it doesn't really affect me all that much. So that's why. But anyway, x to the power of k, open parentheses, open parentheses, proving that it's more difficult. Now, x to the power of k, open parentheses, x to the power of negative 1, close parentheses, open parentheses, x to the power of negative 1, close parentheses, k to the power of k, which is equal to, okay, am I missing a step? Let's check this. Okay. X to the power, yeah, which is equal to x to the power of k times 1 times open parentheses x to the power of negative 1 close parentheses, x to the power of k times 1 times open parentheses x to the power of negative 1 close parentheses to the power of k is equal to x to the power of k times open parentheses x to the power of negative 1 close parentheses to the power of k. Right. A lot of work to get there, but I mean, showing each step is a valuable or rigorous thing to do, even though within practice a lot of the stuff that's gone over within research, at least from what I hear, is encapsulated, which makes sense. Like, why would you want to go over every single minute detail that's not exactly important to the major thing that you're talking about? I mean, in this case, it makes sense because you're looking at Dummett and Foote, and it's like, well, you kind of want that practice, that strength, that potential strength of rigor to draw from. So, I'm talking too much on that. Let's proceed to look at this. To the power of k by the inductive hypothesis. X to the power of k times open parentheses x to the power of negative 1 times OL to the power of k is equal to 1. Hence, we have open parentheses x to the power of k plus 1 close parentheses times open parentheses x to the power of negative 1 close parentheses k plus 1. That is equal to 1. So, well, still more work to be done. Because we forgot to, well, there's just this last little bit, which is, therefore, x to the power of k plus 1, open parentheses x to the power of k plus 1, close parentheses to the negative 1, is equal to open parentheses x to the power of negative 1, close parentheses to the power of k plus 1. And so, by induction, open parentheses x to the power of a close parentheses to the power of negative 1 is equal to open parentheses x to the power of negative 1 close parentheses to the power of a, which is equal to x to the negative a, and this is for all a greater than or equal to 1. So we have it. So let's check to make sure we haven't missed anything. Plus 1, pushing up through here, that looks good. Is equal to x, so that holds, rearrange it, and hypothesis, x to the k is, let's make sure that looks like a 1, x to the power of k, open parentheses x to the power of negative 1, close parentheses to the power of k, hence, open parentheses x to the power of k plus 1, close parentheses, open parentheses, x to the power of negative 1, power of, what is this? Why did I make it look like that? K plus 1 to the power of k plus 1 is equal to 1. Right, okay, so therefore, okay. Yes. That should be a separate point. I think, yeah, I don't have anything else to say on this. I think that's pretty solid. By induction, x to the power of a to the power of negative 1. Equals x to the power of negative 1. to x to the power of negative a. Yeah. Okay. Now let's go on to the next part, which we extend part A to include all of the integers, all arbitrary, well, A, B, such that they could be any sort of integer. Okay. Okay, so part 3, part C. For us to extend, well, we got to prove this. But this holds for this group here. More explicitly, we're just asked to extend the principle that of 1 to all A, B, than the integers. So we'll use the conventions. I suppose conventions is a way of putting it, but it's more so conventions inherited from what, right? So inherited from the integers themselves, inherited from, what is it? The implicit things that we know to be true outside of the context of what this is, right? So we use the conventions x to the power of 0 is equal to 1. And x to the power of negative n is equal to open parentheses x to the power of negative 1, close parentheses to the power of n for n greater than 0. So we want to be able to take account. So we already have the positive integers taken into account. So we want to break this up into the cases where we take into account 0 cases, right? And instances of mixed signs and just negatives in general. So we're going to start with 0 cases. And we're done because there's 0 cases now. But for any integer, a, x to the a plus 0 up to the a plus 0 is equal to x to the a, which is equal to x to the a times 1, which is equal to x to the a times x to the 0. So, and then like we could swap this around, right? We could swap this around such that we have, so that's like saying, you know, b is equal to 0 in the, yeah. So we could also have, we could also have the case in which, you know, for any integer b, right? And then we could have a be fixed to be 0, so we had x to the b, which is equal to x to the b, well, 1 times x to the b. All right. Which is equal to x to the power 0 times x to the power b. So that holds up pretty well. Now let's go on to the case of mixed signs. I guess not. I don't know. Let's see. Let me think about that. Let me think. Okay, so let's see. For mixed signs, we have a is greater than 0, b is less than 0. Let's take that case. A is positive, b is negative. Let's write b to be equal to negative m with m in positive integers. If a plus b is equal to a minus m is greater than 0, then x to the power of a plus b times x minus b is equal to x to the power of a minus m times x to the m, which is equal to x to the power of a minus m plus m. So yeah, x to the power of, open parentheses, a minus m plus m. Just good practice to kind of get that on line. And then is equal to x to the a, which implies x to the power of a plus b is equal to x to the a, x to the b. So yeah, we multiplied on the right by x to the negative b is equal to x to the power m, x to the m I mean to say, and used the positive exponent law from part 1 from a, yeah, so there we go. So let me pause right here real quick. All right, so go from x to the a plus b times x to the negative b, which is equal to x to the power of x to the a minus m times x to the m, which is equal to x to the a minus m, well, open parentheses, a minus m, close parentheses, plus m, which is equal to x to the a, which implies x to the a plus b is equal to x to the a times x to the b. Now, let's see if we can look at a different case, well, look at a case within a case. In this case, if a plus b is equal to a minus m, which is less than 0, then negative a plus, open parentheses, a plus b, close parentheses, is equal to m minus a greater than 0. And x to the power of negative open parentheses a plus b, close parentheses, times x to the a is equal to x to the m minus a, close parentheses, x to the a, which is equal to x to the open parentheses m minus a, close parentheses, plus a, which is equal to x to the m, which is equal to x to the negative b. Now, let's write multiply in this case with, so we had that other case over here. Now, let's apply the same sort of thinking over here where we write multiply. Write multiply by x to the negative a, which gets us x to the negative a plus b, well, x to the negative open parentheses a plus b, close parentheses, all of that. Okay. X to the power of negative open parentheses a plus b is equal to x to the power of negative b times x to the power of negative a. Now, take inverses up, well, don't exactly have a lot of space for that. And I'm not tall enough to reach that, so we can't use that. How about this? Right, multiplying. Holds up pretty well. Now, actually, there's enough space. There's enough space before we move on to the next case. Now take inverses and use open parentheses u v to the power of negative 1 equal to b to the negative 1 times u to the negative 1. And part b, right, so part b was about the x to the a, open parentheses x to the a to negative 1 is equal to x to the negative a. So just note that right there. So we can say that we can take the inverses and use uv to the power of negative 1 equals v to the power of negative 1 times u to the power of negative 1. Open parentheses uv, close parentheses to the power of negative 1 times is equal to v to the negative 1 times u to the negative 1. And part b to say that open parentheses x to the power of negative open parentheses a plus b close parentheses close parentheses, the power of negative 1 is equal to, open parentheses, x to the power of negative b times x to the power of negative a, close parentheses, to the power of negative 1. Yes, and from that we can then say that x to the power of a plus b is equal to, open parentheses, x to the power of negative a, close parentheses, to the negative 1, well, that implies x to the power of a plus b is equal to, open parentheses, x to the power of negative a, close parentheses, to the power of negative 1, times, open parentheses, x to the power of negative b, close parentheses, to the power of negative 1, which is equal to x to the power of a times x to the power of b. Alright, now let's step back, take a look at it, make sure it makes sense. Yes, okay. Okay. X to the a times x to the b, which is exactly what we wanted, right? Okay, now let's move on to the next case, mixed signs. Well, actually, let me check this thought of mine. Yeah, that holds. It holds insofar as I can see. If it's wrong, then by all means correct me. And also, like, follows pretty well from the thing I did earlier, which was the, what was it? Kekola's solutions, yeah, so. It's a case within a case within a case. Now, let's go on to another case. So another mixed signs case. This case, a being less than 0, b being greater than 0, sorry, b being greater than 0. This should be, so this is symmetric to the previous case, right? So I guess you could say by symmetry, right? But I mean, the point is, well, this is symmetric to the previous case, but specifically in this instance, you can swap A and B. So the same argument yields x to the, come on, gosh dang it. If only I had perfect handwriting, right? So, yeah, so the same argument yields that x to the power of a plus b is equal to x to the a, x to the b, and we carry on the same form of argumentation as we did there. We just swap the things around, right? So if we just swap the things around, then we get back to where we want to be. Swap the things, what I mean is these specific things. So, but what about the case with both of them being negatives? So if they're both negative, A is equal to negative R, B is equal to negative S, with RS greater than 0. Then A plus B is equal to negative, open parentheses, R plus S, close parentheses, and x to the power of A plus B is equal to x to the power of negative, open parentheses, R plus S. R, B is equal to negative S with R, S greater than 0, then A plus B is equal to negative, open parentheses, R plus S, and x to the A plus B is equal to, yes, x to the power of negative, open parentheses, R plus S, close parentheses. So this would be equal to, open parentheses, x to the R plus S to the negative 1, which in turn would be equal to, open parentheses, x times R times x times S to the power of negative 1. So that's something interesting. Well, I'm not talking about this specifically. I was just thinking about something else while also doing this. So, open parentheses, x to the power of S, close parentheses, to the power of negative 1 times x to the power of, I mean, not to say that this isn't interesting, right? But x to the power of R, close parentheses, to the power of negative 1, which is equal to x to the power of negative S times x to the power of negative r is equal to x to the power of b times x to the power of a. So, shoom, right? So, you should be able to trace that pretty reasonably. This all holds up. Unless if I've made a mistake, which, correct me. In the comments below, that sort of thing. I don't care. It's not life or death. Just say something, and we'll all be the better for it. Even if you're a snob, about it, nobody likes snobs and nobody will like you, but that's fine. Okay. So since x to the power of b and x to the power of a commute with themselves as powers of the same element, commute with themselves as powers of the same element, what can we say then, right? Well, we can say that x to the power of b times x to the power of a is equal to x to the power of a times x to the power of b. So x to the power of a plus b would then be equal to x to the power of a times x to the power of b. Which, feels like we're missing a step, but we've gone through and we've shown this explicitly. So, yeah, and we have that commutativity to our advantage. Now, we established x to the a plus b is equal to x to the a times x to the b, and open parentheses x to the a, close parentheses, to the power of b is equal to x to the power a times b for positive ab, proved that the proved open parentheses x to the a, close parentheses to the negative 1 is equal to x to the power negative a, and extended this x to the power of a plus b to equal x to the power of a times x to the power of b to all integers a, b as required. So we're done with exercise 19. Quite a long exercise it was. Now let's get to exercise 20. Do I have time for exercise 20 in this session? Yes, I do. Okay. Just camera check here. Doing fine. So in exercise 20, we're told that for x, an element in a group G, to show that x and x to the negative 1 have the same order. So intuitively, order n means x to the n is equal to 1. Inverting both sides preserves equality and turns x to the n into open parentheses x to the negative 1, close parentheses to the power n. So the same n works for x to the power of negative 1. Symmetrically, any power that kills x to the power of negative 1 also kills x. So, putting the word kills in there is kind of a brutish thing, but I mean, terminates? I mean, well, it's just an easier word to say. But let's get into the meat of it to try and show more rigorously what we have with intuition. So, recall the order of x is the least n within the positive integers. Great, yeah, the positive integers with x to the power n equal to 1 if such an n exists. Otherwise, the order of x is equal to infinity. So, I mean, just kind of infinity is a weird thing, but so we want to show, the finite order case in both inequalities and then note the infinite case. Yeah, because we have to go over both the finite and infinite case. Otherwise, it's just we're not doing what the question is asking. So then note the infinite case. So if the order of x is finite, then the order of the inverse of x is less than or equal to the order of x. Let's show this a bit more in depth. We can't just sort of say things and have them be true. That would be nice, but so let the order of x be equal to some n. Then x to the power of n is equal to 1. Taking inverses on each side. We've got that open parentheses x to the power of n, close parentheses to the power of negative 1 is equal to 1 to the power of negative 1. Now, what can we do here? Well, let me do this. Carton this off. Well, from here, we can use that trick that we used earlier, using open parentheses uv, close parentheses to the negative 1 is equal to v to the negative 1 u times u to the negative 1 we can use that repeatedly or just from that directly from that instance I'm referring to where we use this trick, the open parentheses x to the power of a to the power close parentheses to the negative 1 is equal to x to the negative a, which is what I mentioned earlier. We can use this repeatedly. And so what does this look like? Well, we have x to the, open parentheses, x to the power n to the power negative 1 is equal to, open parentheses, x to the negative 1 to the power 2n, and one to the power 1 to the negative 1 is equal to 1. So from that, from both of these parts that we get by breaking it down with this trick, you know, you could write this more explicitly, and here go x to the power, x to the power n, something like that. No, not like that. Well, suffice to say, you could, if you had more space, you could do that. I'm gonna have to write really small, but yeah, you can apply this trick here, which we used in exercise 19. Use that, well, in this case, have to, if you want to prove it, which is what's going on right here. Show this, connect both of those individual pieces, and what we get is, open parentheses, x to the power negative 1, close parentheses, to the power n is equal to 1. So from that, we can then say x to the power negative 1 has finite order. And x to the power of negative 1, the order of that, is less than or equal to n, which is equal to the order of x. But yes, the purpose of splitting it into this, and then the later thing is to show that they are indeed equivalent. Which I think I still have time for. Let's do a quick camera check, make sure everything's going well on this end. Good. Right. Now, going on to the next part. want to look at this case. If the order of the inverse of x is finite, then the order of x is less than or equal to the order of its inverse. Let the order of the inverse of x equal k. Well, then, open parentheses, the inverse of x to the power k is equal to 1. Taking inverses, the open parentheses, the inverse of x, close parentheses, to the power of k, close parentheses, to the negative 1, is equal to 1 to the negative 1. Again, using the inverses law for powers, right? So that trick that we looked at earlier, again, using the inverse law for powers, open parentheses, x to the power of negative 1, close parentheses, to the power of k, close parentheses, to the power of negative 1 is equal to x to the k, and 1 to the power of negative 1 is equal to 1. So x to the power of k is equal to 1, and therefore x has finite order and the order of x is less than or equal to k, which is equal to the order of its inverse. And combining the two inequalities in a finite case, let's write this down. Combining the two inequalities in the finite case yields that the order of x is equal to the order of the inverse of x. Right, so we showed each of these cases. And so we're able to say that, hey, the order of x is equal to the order of its inverse. And if this is sort of its own separate piece, the infinite case, right? So if x had infinite order, but its inverse finite, or vice versa, by the arguments before, we'd get a contradiction. So try to use the basic inequality argument for each case, and for each case you would get a contradiction. Yeah, but it's by definition of what order is, right? So the order of x is the least n within the positive integers, such that with x to the power n equal 1. So we have a contradiction. Hence, x has infinite order. Now, there is a more rigorous way to go about this, right? You write that out, but I'm running out of time as it is, and plus it's sort of just, it's like kind of like, it's a bit of a cop-out, like how the bisymmetry thing is a bit of a cop-out because you don't have to write all of the things, but this is kind of what that is. X has infinite order if and only if its inverse has infinite order. Therefore, finish off all the way over here. Therefore, x and its inverse always have the same order. X and its inverse always have the same order. And that is all for now.